Okay, we'll start the session. In the previous class, we have discussed about the NVIC. NVIC. What is NVIC? Nested Vectored Interrupt Controller. Interrupts need to be controlled. The ARM Cortex M3, it is having the process of controlling the interrupts. The interrupts may occur. There are 5 categories comes into picture. It is closely coupled to the processor. NVIC is closely coupled to the processor core, and provides the number of features as follows. I am not going to discuss once again here. I am just giving the what and all the different types of nested vector interrupt controller. First one is nested interrupt support. If any interrupts are nested, it will give the support for that one. It can handle that one. Vectored interrupt support. List of the interrupts are there. One after the other, one after the other. You can handle that one also. Dynamic priority change. Priority to handle the interrupts. It can dynamically change that one. Priority can be changed based on the privilege of that particular interrupt. Reduction of interrupt latency is one more category, where since dynamically you are dealing with that one, since we are going to deal with the nested interrupts, we can reduce the latency of handling the interrupts also. And the last one, if the interrupt is not that much important, that can be masked. If the interrupt is not that much important, if it can be masked, it will mask it and it will move ahead for the next operation. These are the 5 different features where NVIC can support, or your ARM Cortex M3 can support the interrupt handling itself. Already it's been discussed. We'll move ahead with the next topic. Very important. We need to know that one. What is the total memory which is available in ARM Cortex M3? See, every processor, advanced processors, we can say, previously when 8085 was introduced, at that time there was no internal memory at all. There was no internal memory where we cannot keep the data. But later stages, some of the processor which is designed, which is fabricated, which is introduced, they will be having some internal memory to store the data and also to store the code itself. So as the technology move ahead, as the requirement changes drastically or dynamically or exponentially, there was a requirement for memory with the processor itself. So ARM Cortex M3 is also having some memory, even though it is not very big, sufficient memory is available over there itself. So Cortex M3 has a predefined memory map. You should also know that one, how exactly the available memory is been mapped. Available memory, some set of memory is there. It's been given as 4 GB memory space. Totally, it's going to have the 4 GB memory space in the ARM Cortex M3. Out of that 4 GB, for what purpose some set of memory has been allocated, and assume that one I need to store the code. If I want to store the code, what is the memory which is available for code? Or if I want to have a stack, what is the memory available for stack? Or if I want to deal with the external operations, what is the memory available for the external operations? All those things has to be mapped over there. So let us see one by one how exactly the existing memory of 4 GB is being mapped inside your Cortex M3. This allows the built-in peripherals. We already know that one ARM Cortex M3 architecture, in that one some peripherals are already built in. Some peripherals externally we are going to connect that one, but some peripherals they're all built in that one. So those built-in peripherals need to have some memory space, need to be connected through some buses. Some of them they're having the peripheral bus, some of them they will be having the memory bus. We have 2 different categories of buses and system bus also, 3 categories. One is the system bus, peripheral bus, and also built-in bus itself. Okay, we'll see to that how exactly. This allows the built-in peripherals such as the interrupt controller and the debug components to be accessed by simple memory access instruction. We ran the interrupt controller in the processor. How to access that one? What is the memory which is available for that? And also it's having the peripherals. Different peripherals are there. How to access that one? What is the memory which is given to that particular peripheral devices? The most system features are accessible in C programming code. Usually, if you are good in C program, you can write the C program. Finally, later you can convert that one to assembly level language program, and then it can be dumped into the ARM Cortex M3. Usually, most of the time, it is made easy such a way that one Chandrakant. Mohit. Most of the time, the program, since uh, most of the users, they feel difficulty to write the program in assembly language. What is the one of the helping done by the developer or the manufacturer? They could able to relate, or they could able to get the C code, and the C code can be converted into assembly language program. If you have done in, I don't know whether in your microcontroller lab you did a C programming or not. Have you written the C programming in your microcontroller lab previous semester, fourth semester? C programming? Yes, you did the C programming, then you have executed that one. You have generated the hex code. Hex code has been generated. There was an option for generating the hex code also. Then that hex code has been transferred to the actual external component, external device what you have connected over there, the peripheral. Usually we write the program in C, then we execute that one. At the time of execution, we will give the instruction saying that one convert or generate the hex file, generate the hexadecimal file. That means it will convert the actual C programming into the your microcontroller programming. Okay, it will be in the assembly language going to convert that one. Then once the assembly language program has been converted, that assembly language program we are going to dump to the external peripheral what we have connected. We might have connected the stepper motor interfacing circuit. We might have connected the elevator interfacing circuit. We might have connected the LED interfacing. We might have connected the LCD interfacing. We might have connected the DC motor. What are the different experiments we have done? Okay, all are having the different kits over there. C programming, convert into X file. That X file has to be dumped into the peripheral interfacing circuit. Okay, then only that hardware is going to execute that one. Because I have a system. In the system, I'm having a Keil software. In the Keil software, I'm writing the C program. But peripheral device, I'm having a ARM Cortex microcontroller or microprocessor. This microprocessor cannot run the C program as it is. This microprocessor cannot run the C program as it is. It needs a hex code only. So you need to convert that C program into hex code, and that hex code has to be dumped or burned into the hardware. Then those program is going to be executed. It will execute and will run the peripheral device what you have connected over there. The predefined memory map also allows the Cortex M3 processor to be highly optimized for speed and easy of integration in SoC, system on chip. Entire system is available only on a single chip. Entire system in the sense, including your hardware, software, everything, including one chip is available. Use that chip and execute that. We call this a system on chip. Okay. So entire computer can be kept on one chip itself. We call this a system on chip. Overall, a 4 GB memory space can be divided into range. Different ranges are there. We will see that one how exactly a 4 GB is going to be divided. See here, this is what the memory mapping. The memory 002 FFFFFFF. So that indicates that one 4 GB memory which is available. This 4 GB, the 4 GB what is available, that is been divided. So the lowermost memory, that is 0000002 1FFFFF. Okay. So this much memory. Now I want someone to take your calculator and convert that one FFFFFF. What is the value of that one in decimal? 1 triple F 4 Fs. Convert that one into decimal. 1 3 Fs and 4 Fs. 1 3 F 4 Fs. Total is 7 F. What is the decimal value of that? Error? 5. Is that correct? Decimal value? Divided by 1024. Five two. Just a second. This much. 524 287. Let it be. Something it's okay. It's changing. Okay. We have overall 4 GB memory space in the ARM Cortex memory. In that one, lower memory is used for the code. Now we need to know how much memory is used for the code itself. It is showing as 53 crores 68 lakhs 70,911. It's the decimal value what we are getting over here. So this is the number of bits. This is the number of bits are there. We have converted that into actual hexadecimal code has been converted into decimal value. This is the number of bits are there. But I don't want bits. I want to get it in kilobytes. I want to get the value in kilobytes. How to get the value in kilobytes? You should divide it by 10,000. Divide it by 1,000 if you do that one. You're going to get something like 53 kilo. 53 kilo you are going to get that one. 53 kilo. 53. Okay, 5.3. 5.3 kilo you are going to get. That much memory you are going to have for code. In ARM Cortex M3, code can be stored with the lower order 5 divided by 3. 0.5 mega is coming. 0.5 mega bytes of memory is going to be used for code. Similarly, the same size of memory is being given for SRAM. Next to that one, we are going to have the next memory, that is SRAM. Once again, for peripherals, next memory is being allocated. But for external RAM, we have more memory. External devices, we are going to have the same set of memory. And similarly, for system level programming, we'll be having the memory. So overall, 4 GB memory has been divided into 6 categories. One is for the code, second one is for the SRAM, next one is for the peripherals, external RAM, external device, and external level will go for that. ARM Cortex M3 design as an internal bus infrastructure optimized for its internal memory usage. In addition, the design allows these regions to be used differently. It's used for different purpose. Data memory can still be put into the code region. Why? Why they are saying data memory can still be put into the code region? Any you can think about it. Why the code and data can be in the same memory? I've told this one many times. The architecture. What is the architecture we are using? What type of architecture? There are two different types of architectures are there. Harvard architecture is there. In Harvard architecture, though we are going to have the two different buses which are used for one is to extract the code, one is to extract the data. But when I have a single memory, in the same memory we can keep the code and also the data. But there is one more architecture called the random architecture, where the one of the two separate memories are available. One memory dedicated for the data, other memory is dedicated for the code. But here, this architecture, ARM Cortex M3 is using Harvard architecture with a single memory can be used for storing the data and also the code. Okay. The system level memory region contains the interrupt control and also debug components. So once you know that particular table, you can easily explain what are the 6 different categories of the memories. By having fixed addresses for these peripherals, you can port applications between the different Cortex M3 products much more easily. There are several bus interfaces on the Cortex M3 processor. They allow the Cortex M3 to carry instruction fetches and data access at the same time. Code memory bus, system bus, peripheral bus. I told you, code memory bus, a bus is mainly used to access the code and data. System bus is mainly interconnecting the internal parts or internal peripherals of your ARM Cortex M3. Peripheral bus totally dedicated for external peripheral devices which are connecting. If you want, you can go back to the architecture. There you will come to know what are the different buses we are going to have. Basically, three different buses are going to be used. One is for system. The internal system components need to be connected. Second one is code memory bus, where you need to extract the code, you need to dump the code. Both the operations can be done. And the third one, peripheral. Any peripheral need to be connected. I need to connect the USB. I need to connect the system. I need to connect some other like stepper motor, I can connect using that peripheral buses. It is having the memory protection unit. It's optional. The unit allows access rules to be set for privileged access. Which one need to be accessed? It should be given the privilege. Fault exception is generated when any violation comes into picture. Rules are there. If you are having violation with respect to the rules, a fault exception comes into picture. Base primary, fault exception, and also we are going to have the primary mask. 3 different types of masks are there. Whenever there is a rule has been overruled, means violated, a fault exception is going to be generated over there. MPU can be used in various ways. It can be used in various ways depending on the requirement itself. So this is memory map. Whenever there is a question asked for the memory map, it may be asked for 4 marks. You should know that one. What is the overall size of the memory? That is 4 GB memory. In that 4 GB memory, obviously going to be different divided. Totally, there are 6 categories are there. One is for code, another is for peripheral, another is for SRAM. These 3 we should know. Another 3 is for external operations. Okay, external memory, external device, external peripheral. We'll call them. Okay. Next is very important, instruction set. Already you started writing the program. You might have used some instructions over there. Base instructions are general instructions are not been explained here because you know what is the general instruction. You already come across the general instruction like move instruction, LDR instruction, SDR instruction. All those things you come across. One more instruction called B. B is also an instruction. B is also an instruction. Don't think it's a simple character in the program. Likit. B is also an instruction. What is B? You have started writing the program. Yes. You have done the program. You have typed the program in the lab, but you didn't get the output. I know. But you should know the instruction what you have used. You have used the LDR instruction. Yes or no? Have you used the LDR instruction in the lab? Yes. Have you typed the program? You are in front of the system, you typed the program? No. Area is one keyword you have used. You have used the area. You have used the LDR instruction. You have used the SDR instruction. Have you used the move instruction? No. Only LDR and SDR only have used. After that one, you have used one more instruction. Here, be here. Have you used that one? Here, be here. This is an instruction. B is an instruction which is available in your ARM Cortex M3 or ARM. In ARM, B is an instruction. B indicates branch. B means branch. What do you mean by branch? It is saying that one, this instruction is used to jump to this particular label. B is an instruction, jump to this particular label. It is saying that one, wherever this label is there, go to that instruction. I'm having LDR, I'm having LDR, I'm having LDR, and later I'm having the B is the instruction. Last but one instruction is this one, I think so. And after this one, I'm going to have the N. If you're having the lab manual or something, you will have checked it. I'm having so many instructions here, and I have given the instruction called B. B is the branch instruction. This branch instruction is trying to jump to this particular label. This is the label we are having. You have used the labels in the program. Loop 1, loop 2, L1, L2. In your microcontroller lab, you have used that one. Okay. Loop. What do you mean by that? This instruction trying to jump to this particular label. Where is the label? In the same line it is there. Okay, I will give one more LDR. LDR, some STR, something. I'm going to use B next. LDR, STR, next. This instruction is executed, this executed. When it comes to this, branch to this particular label. What it will do? It will straight away jump to here. Without executing these two. Without executing this instruction, it will straight away jumps to wherever the next label is there. Correct now? You will use this one. Jump instruction, simple jump instruction is going to be. There you are using jump instruction, your microcontroller or some other processors. But here there is a branch instruction. What it is doing? Go to this particular label. So here it is easy to understand that when we are going to this particular label. So it will straight away go to the label which is available next. But in this case, what is happening? Branch to this particular label. Branch to this particular label. Where is this label is there? This label is here only. The same line. Once again, the same line comes. Same line. Infinite times it keep on going to that particular label only. That indicates that one, no need to go anywhere else. Stop your program. What it is giving? Means you are not properly indented. I told you clearly that whenever you are writing your ARM programming, indentation is very, very important. All the labels should come on the extreme left side. Instructions should come with one indentation, and after that one, whatever the variables or registers you are going to use, you should write it at the right side itself. Okay? Even a comma is missing, it's going to give the error. Even a semicolon is missing. Actually, we don't have a semicolon. Only for the common purpose, we are going to use a semicolon over there. If you are writing the labels should be at the extreme left side of your screen. If you are keeping this here, then you are going to get the error. That's why see, I have done the LDR here and the label I am writing on the left hand side. Even you are going to have the start. You are going to have the end. So start should be at the leftmost side of the window. Even you maybe having one more thing, start. Entry is there. All your labels should be on the extreme left side of your editor screen or editor window. If you are keeping the start very close to or the same indentation of your instruction, you are going to get the error. Similarly, these LDRs also should not come to the left side of your editor window. Most of the time, even we are, since many years we are saying the same thing. Even your record book also you are going to write everything on the left hand side. Always in your record book, when you are writing your programs, this is your sheet, this is your border, what you are going to have that one. Take one pencil and put one line here. Using one pencil or line. All your instructions should come in the right side of your this line. All your labels should come in the left side of this line. Okay, so this is border. Leave this one. From this border line, here I should get start. I should get entry. I should get L1, L2, L3 here. All these labels should be on the left hand side of your pencil line. Then all the instruction LDR, STR, move, all these things will come on the right hand side of your window, or pencil line. ಇವತ್ತು ಹೇಳಿದ್ರು ನಾಳೆ ದಿನ because students are not worried about writing the program, simply they are copying from somebody else in a hurry, they will write the mistakes. Okay. ARM Cortex M4 version, key version M4, download. I keep on repeating that one. I don't know how many of you have downloaded that one. M4 or M5? M5. Good. Write a small program, a simple program, move or LDR. Try to execute that one. You will come to know what are the errors you are going to. Even last year also I told you, do the mistakes. repeat, get the errors. You should do that one. Okay. Instructions, because this is very, very important. I'll just give the glimpse of the instruction set. Basically, we know that when there are two types of instruction set. One is the ARM instruction set, another is the thumb instruction set. In the previous version, we are having only thumb instruction, but in ARM Cortex M3, we are going to have the thumb 2 instruction. Thumb 2 instruction, it can take care of the 16-bit instruction also, 32-bit instruction also. Previously, thumb instruction, it was having only 16-bit, but now thumb 2, it can go for 16-bit instruction also, it can take care, 16-bit data also, it can take care, Tejas, and it can also take care of the 32-bit instruction also. A thumb instruction, it was taking care of only 16-bit, but thumb 2, it can go for 16-bit, it can go for 32-bit. There is no difference. ARM instruction, always it is 32-bit. ARM instruction, always it will take care of the 32-bit instruction. But sometimes I need to deal with the 16-bit data. Sometimes I need to deal with the 32